A very good day to our lecturer. Before we start our presentation, let me introduce myself and my teammate. This group consists of 4 members, which are me, myself, Emily Jara Thomas, FAUZAN, EDZAM, and IZZATI. The chapter that we choose for this assignment is Chapter 3, Oscillation. So what is oscillation? The method of repeatedly varying a quantity or measure with respect to its equilibrium value throughout time is called oscillation. Another way to describe oscillation is as a periodic change in a material between two values or around its central value. Periodicity or a recurring pattern of movement or displacement is the fundamental characteristic shared by all of these occurrences. John 2019 stated that sine and cosine function can be used to describe the motion of a simple harmonic oscillating system when the restoring force acts in the opposite direction as the displacement and is directly proportional to it. Consider a weight fastened to a spring as an example. The weight is in equilibrium. When it is at rest, there is a net restoring force on the mass with potential energy if the weight is brought down. When it is released, it acquires kinetic energy and momentum, continuing to move past the equilibrium point and accumulating potential energy or restoring force, which will cause it to oscillate downward once more. In this case study, we will be able to study about linear restoring force in harmonic motion, explain about energy consideration in harmonic study, and learn about them harmonic motion.
Today I'm going to present about linear restoring force in harmonic motion. So firstly, we're going to talk about Hooke's law. In Hooke's law, it stated that in a simple harmonic motion system, the displacement of a spring will be directly proportional to the restoring force, which will be directed to the opposite direction of the displacement of a spring. So the formula for the displacement of a spring is equal to negative kx, and k is the spring constant of a spring, which can also be represented by 2a. So the formula can only be applied on the oscillator in the horizontal system. So next we're going to see the initial condition. So from the formula which is written below the law definition, we can see that there is a equation of velocity in sinusoidal, where omega naught a cos in bracket omega naught t plus p naught. So in initial velocity, the t is equal to 0, so cos 0 equal to 1. So we'll be left with v naught equal to omega naught a. So we rearrange the equation, we can get the amplitude is equal to v naught over omega naught. So next we're going to see simple harmonic motion as the projection of a rotating vector. So in this section, we're going to find the d theta, so which is the definition of the angle in the uniform circular motion. So as we know, if we differentiate theta into property, we get omega. And to find the d theta only, we need to multiply w with t. So to complete the equation, we need to add the change of theta with the equilibrium angle. So since simple harmonic motion is sinusoidal and bounded, we can be represented by equation of the geometric, which is sinus or cosine. So to find V max, we need to integrate differentiate the equation of x and make the cosine equal to 1 or sine equal to 1. So we get the V max is equal to negative a omega naught, while a max acceleration maximum is equal to a omega naught squared. So omega can also be represented by 2 pi f, and also it can be represented by square root of k over m. Since we know that frequency is inversely proportional to period, we can find that the period is also equal to 2 pi over omega naught. So next we're going to see the effect of constant external force on a harmonic oscillator. So in this section, we're going to investigate the simple harmonic motion when the oscillator in vertical position. So as we know, in vertical position, the spring will be dragged down a little bit by the mass that is attached to it because of the gravitational force X on it. So we have to add one force to the formula, which is mg. So the formula for oscillators when it is vertical is equal to negative kx plus mg. So since at equilibrium, the spring will be dropped down a little bit, it will create new equilibrium position. So we need to find this new equilibrium position. So to find the new equilibrium position, we need to let f equal to 0, since at rest the f is equal to 0. So we write the formula where 0 is equal to negative k in bracket xe prime, which is the new equilibrium, minus xe, which is the old equilibrium position, plus mg, and we get the new equilibrium position is equal to xe plus mg over k. So the new formula when the oscillator in vertical position is equal to f equal to negative k in bracket xe x, which is the displacement, minus xe prime plus mg. So
I'm going to continue presentation of the subtopic of 3.3, which is the energy consideration and harmonic motion. So basically in this subtopic, we need to understand two types of energy, which is kinetic energy and also potential energy. So if you want to understand about the harmonic motion, you need to think about the harmonic motion is when a system that moves back and forth around a central or equilibrium position. So this type of motion is often described by a sinusoidal functions like sines or cosines. You can see this type of motion in a lot of different physical phenomena like the oscillation of mass spring system and also a pendulum. So basically kinetic energy is half mv squared, where m is a mass and v is velocity, where kinetic energy is energy associated with motion. An object oscillates, its energy velocity varies. So during motion, the kinetic energy is maximized at the amplitude and zero at the equilibrium position. So for potential energy, it is U is equal to half kx squared, where k is spring constant and x is the displacement. So potential energy is the energy associated with an object positioned in the force field. So potential energy is maximized at the amplitude and is zero at the equilibrium position. So in the conservation of the energy in the harmonic motion, we can see the summation of the combination of the potential energy and the kinetic energy, which will produce after this derivation, it will produce energy total is equal to half ka squared. Thus, the total energy in the simple harmonic motion of a particle is directly proportional to its mass, directly proportional to the square of the frequency, directly proportional to the square of the amplitude of the oscillation. Last but not least, we can see about the graph of energy visualization, where at the mean position, the total energy in the simple harmonic motion is purely kinetic, and the extreme position, the total energy in the simple harmonic motion is purely potential energy. Where at the other position, the kinetic and potential energies are interconvertible and their sum is equal to half ka squared. Therefore, varying velocity causes a turning point in oscillation. The transition happens at the maximum equilibrium displacement. It reverses so fast in these crucial seconds, the item briefly stops moving. So reaching zero velocity, the highest divergence from equilibrium or amplitude defines the turning moment.
Now I will proceed to the next subtopic, which is damped harmonic motion. The damped harmonic motion oscillation is a type of motion that occurs when a system experiences a damping force, which gradually decreases the amplitude of oscillations over time. This type of motion is characterized by the presence of a damping term in the equation of motions, which opposes the oscillations and causes them to decay. So this figure is the model of damped harmonic oscillator. In a damped harmonic motion oscillator, the equation of motion is given by the first equation, where m is the mass of the oscillator, b is the damping coefficient, k is the spring constant, and x is the displacement of the oscillator from its equilibrium position. As with the undamped case, we divide the equation 1 by m to obtain the second equation. If we substitute the damping factor y and omega into the second equation, it's assumed the simpler form in the third equation. The problem is complicated by the velocity dependent factor to y x dot. It is verifiable by attempting that simple sine or cosine solution do not work. For second order differential equation with constant coefficients, a method of solutions was presented that worked rather well. Considering the differential operator d over dt as d, we operated on x by selecting a quadratic function of d in a way that satisfied the equation 4. Writing the equation in that form simplified it when we factor the operator term using the binomial theorem, which produced the equation 5. The general solution was a sum of solutions derived by putting the outcome of each first-order operation on x equal to 0 because the order of operation was arbitrary. Consequently, we got the sixth equation. In this topic, we have three types of damped harmonic motion. First, we have overdamping. Overdamping occurs when the damping coefficient is greater than the undamped resonant frequency. In this case, the system moves slowly towards equilibrium without oscillating, which means Q is more than 0. Second, we have critical damping. Critical damping is a condition where the damping of an oscillator causes it to return as quickly as possible to its equilibrium position without overshooting, which means Q is equal to 0. And the last one is underdamping. Underdamping is occur when the damping of an oscillator causes it to return to equilibrium with the system oscillating at a frequency marginally different than the undamped case, and the amplitude decreases gradually, which means Q is less than 0. The next subtopic is energy consideration. Energy consideration are important in damped harmonic motion oscillation because the presence of damping force causes the system to lose energy over time. The rate of energy loss is greatest at the time of largest velocity and hence largest damping. The total mechanical energy of the system, which is the sum of the kinetic and potential energy terms. As we can see here, the total mechanical energy of the system is in the equation 1. As previously mentioned, this was constant for the undamped oscillator. Let's distinguish the previous expression according to T in the second equation. Previously, the third equation was the differential equation of motion. As a result, we could write for the time rate of change of total energy in the fourth equation. This was determined by multiplying the damping force by the velocity. Like the amplitude, the total energy ultimately became negligibly small because this was always either 0 or negative. Due to the viscous barrier to motion, the energy dissipates as frictional heat. The last one is quality factor. Quality factor is a dimensionless parameter that quantifies how good an oscillator is in damped harmonic motion. The Q factor is defined as the ratio of the energy stored in the oscillator to the energy loss per cycle due to damping. The Q factor is related to the damping coefficient and the undamped resonant frequency of the oscillator. The less damping there is, the higher the Q factor. The Q factor is a measure of the sharpness of the resonant peak and the rate of energy loss. A high Q factor indicates a narrow resonant peak and a slow rate of energy loss, while a low Q factor indicates a broad resonant peak and a fast rate of energy loss. The Q factor is an important parameter in many applications, such as in the design of filter, sensor, and oscillator. The average rate of energy dissipation for the damped oscillator is given by E dot equal to negative C x dot square. So we need to calculate x dot. So from the first equation, we can differentiate it and we obtain the second equation. The third equation is the energy loss during a single cycle of period T d equal to 2 pi over omega d. The integral of both sine square theta and cos square theta over one cycle was pi, while the integral of the sine theta cos theta product vanished. Thus, we had the fourth equation, where the relations between omega and y had been used by determining the damping factor y in relation to a time constant such that y, we could determine the magnitude of energy loss inside a single cycle. And we can obtain the fifth equation. Where the oscillator store energy was at any given moment, we can define the sixth equation. It was evident that oscillators' residual energy dissipate exponentially with time constant during every given cycle. Consequently, we could observe that the quality factor Q was equal to simply 2 times the inverse of the ratios provided in the previous formula or in the seventh equation. So the oscillation period T with weak damping was substantially less than oscillation time constant, which represented the oscillator's rate of energy loss. Q was large in this kind of situations.
In conclusion, the term vibration used to describe the mechanical oscillation of an object. However, oscillation also occur in dynamic system, or more accurately, in every field of science. Study about linear restoring force in harmonic motion, energy consideration in harmonic study, and them harmonic motion have been successfully explained in this assignment. Simple harmonic motion, SHM, is the motion of an particle traveling in a straight line with an acceleration whose amplitude is proportional to the distance from the fixed point on the line and whose direction is always toward the fixed point. The kinetic energy is quadratic in the velocity variable, while the potential energy is quadratic in the displacement variable. The average kinetic energy and potential energy are equal. Therefore, the average energy of the oscillator is equal to its total instantaneous energy. In damped harmonic motion, DHM, an extra damping force dissipate energy and stop the vibration by acting in the opposite direction of the object velocity. Overdamped, critical damping, and undamped harmonic motion are the three different forms of damped harmonic motion. Overdamped is when Q real more than 0, while critical damping is when Q is equal as 0, and underdamping is when Q is less than 0. I think that's all from us. Thank you for watching.